Good morning, everybody. Thank you for joining today's STEM Career Talk. My name is Edith Lai. I am the Digital Media Specialist for the Government and Community Relations Office K-12 STEM Education and Outreach team. So as a reminder, this session is being recorded. In addition, there is a live transcript option. If you want to view transcript, there's an option at the bottom of the webinar page. So a little bit about Berkeley Lab. Berkeley Lab is one of 17 Department of Energy national laboratories. We are located in Berkeley, California, and for almost 90 years, we've been recognized for our leadership and innovation in team science. As of 2020, we've been recognized with 14 Nobel Prizes and credited with the discovery of 16 elements on the periodic table. This Career Talk series is just one of many ways that we like to share our research and our work with the public. So this Career Talk series in the fall has included topics such as STEM and art, cybersecurity and data privacy, fieldwork and travel for research, quantum, and now bringing science solutions to the world. All of these past sessions have been recorded and they've been uploaded to our website if you're interested in viewing those. And in 2021, we will be having more career talks, so make sure you keep checking our website if you're interested in hearing about other fields or other avenues of science careers. Today's talk is about bringing science solutions to the world. Our panel of speakers are engineers who combine their technical expertise with creative problem-solving skills to tackle big issues around the world, such as climate change or fire or other issues. Our first speaker is Dr. Jessica Granderson, a staff scientist here at Berkeley Lab. So Jessica, if you would like to unmute and turn on your camera, please go ahead and introduce yourself.
Good morning, everyone. I'm Jessica Granderson. I'm a staff scientist here at Berkeley Lab. I'm Deputy Director of the Building Technology and Urban Systems Division. And next slide, please. Thank you. My trajectory or path started in high school. I went to public high school. It was there where I was introduced to engineering through a program that was meant to channel students of color into STEM. That was my first glimpse into what is engineering. I went to Harvard University. Other than my coursework, I didn't have that much exposure to STEM professions. This was before it was quite so commonplace to have a variety of summer internships. So when I would return home for the summer, I go back to standard jobs that I had always held, the local pizza place, stepped up to the more business world, working for the county at the unemployment office. That was incredibly boring. All I did was file papers. In the last year of my undergraduate period, I got connected, fortunately, with an astronomy program and was able to start an internship that was all around development of instrumentation in support of astronomy. So I got to work on a large telescope project at the Apache Point Observatory in New Mexico. By the time I had finished with undergrad, I had this false notion that I wasn't ready to be an engineer, that I somehow didn't know enough. And I also really liked school. So I continued and went to graduate school, starting with a master's degree. I went to UC Berkeley, continued then working in the realm of astronomical instrumentation. And I had a stint at NASA Goddard outside of DC in Greenbelt, Maryland. That time working for instruments for the International Space Station. I really enjoyed graduate school and then decided to continue on for a PhD. I focused in user-centered design and mechanical design theory and methods. I finished my degree and began a postdoctoral appointment at Berkeley Lab. It was a fantastic fit. I never left. I'm still here today as career staff. So I work to make buildings smarter, more efficient, and cleaner. People often don't know that buildings are responsible for almost half of our national carbon emissions. As much as we love the outdoors, buildings are where we spend most of our time. And collectively, we spend hundreds of billions of dollars a year on our PG&E bills. So my team uses a combination of mechanical engineering, machine learning, sensing and automation, and user-centered design to better control our buildings, to find hidden energy waste, and improve the comfort, health, and productivity of occupants. So some of the images I show here just illustrate the analytics tools and new methods we develop. Drones to auto-generate 3D building models and thermal signatures is just one example of some of our current activities. And to make an impact in the world, we directly partner with building owners, operators, utilities, and software technology providers. That's really my day job. Another example of kind of design in action is that outside of my work at the laboratory this past spring, I co-founded Shield the Bay. That's a volunteer team of designers, engineers, and scientists, as well as students. We saw how disproportionately COVID was impacting our communities of color, as well as the systems that serve them. So we engaged Alameda Health System, that includes Highland Hospital, as well as 8 other facilities. And we worked with them to design and scale a face shield product. So we had a direct partnership with the infection prevention team, emergency department nurses, and through that effort, we're able to get a robust solution custom to the needs of that healthcare system, and they're now scaling it for system-wide use. I'll stop there and save the rest for our panel discussion. Thank you.
Great, thank you so much, Jessica. We'll definitely be talking more about how you work with different users and different clients in our Q&A. So our next speaker is Dr. V. Rapp, also a research scientist at Berkeley Lab. V, if you'd like to introduce yourself.
Yeah, so that's a lot of it. My name is V. It said V, not Vi, despite the spelling. I am a mechanical research scientist also at Lawrence Berkeley National Lab. I lead a lot of the combustion research, and essentially what that means is I get to spend a lot of my day playing with fires to try and make them burn better to improve human health. So when I was in high school, I'm not gonna lie, my mom really wanted me to be a doctor or a lawyer. And I looked into both of those career paths and sat on a few panels and realized that it wasn't for me. And a lot of the things that really appeal to me is space. And I'm guessing here that some of you at some point have dreamt about traveling to space or wondering just what's out there. And so when I graduated high school, I was really excited by the idea of finding life on other planets, building technologies to get us there. And as a result, I studied mechanical engineering at the University of Utah. After I guess I should say, similar to Jessica, after I got my bachelor's degree, I didn't feel quite ready to join the workforce. And also the workforce wasn't looking like job hiring in aerospace didn't look really great at the time. So I decided to stay on and do my master's, which was an additional year. After I graduated, there was a huge layoff of jobs in the aerospace industry. I think that year, the local aerospace company had laid off about 20,000 people. So I ended up trying to find kind of the next best thing, which was working on aircraft. And I thought, well, aircraft gets me closer. Hopefully this will get me a tie-in. So I spent about 2 years working for a company called Moog, doing some what they call thermal analysis on flight controls for airplanes. And what that means is I made sure that the electronics didn't overheat, so they'd set the wing, so it wouldn't set the wings on fire and your plane would come crashing down. The funnest part about that job was I got to help work on well, not so new anymore, Boeing 787. It was really exciting to work on. It was really cool to see how that all came together. Unfortunately for me, after spending 2 years there, I realized that it just wasn't going the direction I wanted to go. I wanted to do more with having an impact, helping improve human health, looking at ways that I could actually make our world better. And so I quit my job and thought, well, professors seem like they do a really great job in making the world better and having impact. They get to work with really great students like yourselves and get to work on cutting edge science to help advance us to the next generation. And so I went back and decided to get my PhD. I got it, like Jessica, at UC Berkeley, and I studied mechanical engineering. And because I had already an interest in rockets and designing kind of rocket engines, I decided to study combustion because I figured we all burn things at some level, whether it's using your gas stove, gas appliances, down to driving a car, right, or traveling in an airplane. And I thought by studying combustion, that would give me a broad field to pick from to try and have some kind of impact. And so I studied alternative fuels for combustion engines. And after I graduated, I still felt like I was too far removed from having impact. And so I ended up getting a postdoc at Lawrence Berkeley Lab doing indoor air quality research. And when I got there and I started doing the work there, it was so much fun. I decided to stay and not become a professor and go that route. So that's where I am today. And so a little bit about what I do. As I'd mentioned, we all burn things. I think most of the energy we produce, I think about 86% of it is generated by burning something. And so my main goal was to take my combustion knowledge to help us burn things better to improve human health. Because a lot of the problem with burning things is we create unwanted pollutants or particles. And so, as I had said, as a postdoc, I got to do a lot with looking at indoor air quality and how gas appliances might affect your indoor air quality, especially as you try to make your homes more energy efficient, whether that's through insulation or other means. I also had the opportunity to do some work advancing biomass cook stoves for developing countries. I think about 4 million people die each year from inhaling smoke. And as you can imagine, when we had the fires in California, I'm sure many of you remember how uncomfortable it was breathing the smoke in the air. So imagine if that was kind of your day-to-day. And so our goal was to really help advance these technologies. The nice thing is that work also relates to things we use in the US, such as wood heaters. So I'm also doing some work in improving wood heaters. I still do work in aerospace or on aircraft, but in this case, it's looking at alternative jet fuels. I'm learning how to use machine learning to help us understand how to better predict properties of jet fuels that can be derived from biosources instead of from fossil fuel, and hopefully make that the emissions look a lot better. I also, as I don't know if this counts as a nights and weekends, it's still at the lab, but a side project that's not as combustion related, but still relates to keeping, kind of thermal, keeping things warm, is I worked on it with a team of doctors to develop an infant warmer. A little over 1 million babies die each year from hypothermia, which means you get too cold. And I'm sure, many of you out there with younger brothers and sisters, you may remember when they were babies, it was really critical to keep them warm, right? So you put a hat on them and blankets on them. And in some of these countries where resources are low, they don't have any means to keep infants warm. And it was really inspiring to me to be able to help develop a technology to help keep them warm so that they could survive and grow up. And then a lot of my day-to-day, as I had said, is playing with fires in the lab. And the two burners you see down there are some burners that I helped develop, and for cooking technologies as well as for power generation. So that's a lot of what I do, or I guess I should say a lot of spread of what I do at the lab.
Great, thank you so much for that introduction. And you spoke a little bit modestly because you've also been awarded for your work in the baby warmers. So our next speaker, our third panelist, is Dr. Michael Golner. And Michael, if you could turn on your camera and introduce yourself.
Sure. Hi, everyone. My name is Michael Golner, and I'm an assistant professor and Deb faculty fellow in mechanical engineering here at UC Berkeley. And previous to this, I was at the University of Maryland, and I'll talk a little bit about that. But in my role at UC Berkeley, I advise students and run a research lab, the Fire Lab at UC Berkeley. And you can see one of our flames. And I promise not every researcher gets to burn things every day, but both Dr. Rep and I are really lucky in our careers that we get to do that. So the next slide. So I'll talk a little bit about my career path. I started also, like many others in this talk, at a public high school in Southern California. Probably wasn't the best. We had a couple AP classes, and to me, my sort of favorite class that I really enjoyed was physics. I actually didn't know about engineering as a career. I had done, sort of summer construction jobs and worked at camps. But, the physics class really excited me, and I thought that was what I wanted to do. I actually didn't get into my first choice, which was a private college. And I was actually really excited. I'm also maybe the only one on the talk that didn't go to Berkeley. I went to UC San Diego, and I wound up staying there for my bachelor's, master's, and PhD. And I was really glad about that. One of the great things about the University of California and the large public university system was that there are just so many different opportunities to explore and to change. And so I started in physics and decided, this isn't for me. I mean, I love some of the math, but I wanted to be hands-on, and I wanted to be making a difference, and I wanted to see what I was doing. And I wasn't necessarily patient enough to wait to the fourth year to start applying something in the lab. And so I tried a couple different majors, and far as political science, looking at that, and those weren't the classes I was interested in. And then a counselor recommended I look at mechanical engineering, and I took some of those classes and really loved and enjoyed it. I later interned in a mechanical engineering lab, a combustion laboratory. And that's what really got me started on this combustion path. I have to say, in terms of an opportunity, that wasn't the first opportunity for research that I tried to get into. I can remember asking professor after professor. And in fact, for the lab that I got into, it was maybe the fifth time I asked. And it was for an opportunity that other people had been given. And then I kept asking, and they're like, okay, well, there's another student. Why don't you work with them? And it was sort of that persistence that wound up finding an opportunity. But that's one of the great things about the large universities. There's so many different opportunities when you get there. I actually found an internship, Schirmer Engineering, which isn't around anymore, but was a fire protection company. That was a summer internship. And you can see in the top right, one of the experiments I got to run. I literally got to burn down a warehouse. It's within a laboratory in Chicago. And so they really got me hooked on fire. I actually, I got an internship offer from Lockheed Martin as well, but because everything was classified, I wouldn't really know what I was doing. I always wanted to do aerospace, but then when they told me I could do aerospace engineering applied to burning down buildings, it just sounded so appealing. And so there's a picture of Jonathan, the guy on the left there, was the person who recruited me to the internship and the company. And that completely changed my career path. He actually graduated from the University of Maryland, and that wound up being where I became a professor right after I graduated with a PhD. And so I did that internship for a few summers. They convinced me to stay for a master's, and I did a master's at University of California, San Diego. And then when I was going to leave, I had sort of a pseudo advisor Ali Rangwala, who was there, who was a former grad student at UCSD and then a professor on the East Coast, and my advisor, Foreman, on the bottom, Foreman Williams. And so they sort of convinced me to stay. And the biggest thing for me was that I really loved the environment and the teaching. And I think that's one of the big choices. There's plenty of great opportunities in the company that I was working at. I love what I was doing there, but I enjoyed the research and the teaching aspect a lot more. And so that's why I stayed. And I wound up doing a PhD, and then I was encouraged to apply to faculty jobs and got one. In fact, I had already accepted a postdoc at Berkeley, and was going to do that until the last moment when a faculty job came in. And so there's lots of careers along the way, and they're all great. It just depends on what you want to do and what opportunities come. And then you'll see in a moment with the research that I do, I just recently moved in January to UC Berkeley, back to California, because I work on some pretty relevant California problems. Oh, next slide. And so most of my work is actually focused on wildfires. And so, you know, like Dr. Rapp, who just presented, we both have degrees in combustion. But most of my work, rather than the indoor combustion, is focused on the outdoor combustion and wildfires. And so we often do experiments. Sometimes we do simulations as well, but we're trying to understand how fires spread through vegetation. How do they burn down communities? What's in the smoke that people are breathing? How is it generated? Can we model that? Can we do things to reduce that with prescribed fires? What are the health effects? We also do some other fun things. You saw in the first slide a picture of a little whirl. We do some things called the blue whirl, which we discovered. We use fire whirls to clean up oil spills. And we even do fire safety in space. On the bottom left there, you can see how the difference between how plastic burns on Earth on the left and in space. And even though fires in space are generally much smaller and not as reactive and big, they can actually be much more hazardous because they can burn at conditions that you can't reach on Earth, and they can keep burning without anyone noticing. And so we use sort of the same knowledge we have on all sorts of different problems. And that's what I think makes this career really exciting, is to be able to apply that sort of STEM knowledge to a whole bunch of different practical problems. And we get to put this into practice, whether we're giving advice to CAL FIRE, working with NASA on their tests and how they decide which materials to use, looking at how they clean up oil spills. There's a lot of really interesting situations where we get involved. And many of my students I think is one of the most exciting parts of being a faculty and also as researchers, the people you get to advise, have gone on to careers, everything from being wildland firefighters to city planners, designing big buildings, working at NASA. They've gone to so many different exciting STEM careers. And so I think there's a lot of interesting opportunities in the area.
Thank you so much for that introduction. It's definitely great to see how you can have fun in the lab with different types of experiments. So I'm going to stop sharing, and I'd like to introduce one last speaker. So Elisa is going to be co-hosting this event. Lisa, if you could introduce yourself.
Yeah, thanks, Edith. As Edith mentioned, my name is Elisa Vitale. I'm also part of the K-12 team as a content and instruction coordinator. So I will be monitoring the chat box today. So if anyone has any questions for the panelists, please put them in there and I'll make sure the panelists get to answer those questions. But we also have some prepared questions that we came up with beforehand. So at this moment, I will ask everyone to turn on their cameras again, and we can get our discussion started. There you go. Thank you. Okay. Again, thank you to all our panelists for sharing your stories. It was really interesting to hear. And so my first question is actually about collaboration. I think all three of you touched on working with different people across different fields. So, what collaborations, I just kind of want to know more about, how they take place when designing solutions. So maybe I'll start with Michael, because you just mentioned, fire in space with NASA and like CAL FIRE. So how do these collaborations happen when designing solutions?
Yeah, I mean, I think for most of the problems we work on, collaborations are essential. I don't go out and fight fires in the field. I've never been an astronaut in space, and other people have, or they work with people who have, and they have that experience. And so when you're designing solutions, and we do see it many times, and probably you've seen it in the products you buy sometimes, where you get something or you see a solution and go, wait, that doesn't actually work. And to find something that works, you really have to understand the nuances of how it's used. And so one thing we often work with is everyone wants to model where the fires are going to be and predict, what's the behavior and where is it coming from. But actually getting that information and then parsing that for someone who's like actually fighting a wildfire right now is very, the guys on the ground have tools, they're running, they have backpacks, they're huffing and puffing in smoke. They're not on their phone checking an app. They can't be. They rely on the radio and they do real short clicks. And so, getting that knowledge and how the knowledge that we develop is then parsed to different people is really important. And, I think we've had collaborations, formal ones with medical doctors, with climate scientists, foresters. There's so many different people we've worked with, and they have those different perspectives, and bringing them together, I think, is essential to finding solutions. And that's one of the important things, is just recognizing that you don't know everything, and that when you work with other people, you're there to learn. I find the collaborations really great, and starting them can sometimes be hard. And maybe others can touch on how they get started in finding the people, but a lot of it has been through, networking and different meetings, and even nowadays, networking online, there's still a lot of opportunities.
Thank you, Nicole. Yeah, I love the point that you said, like recognizing that you don't know everything. I think that's an important thing to realize, that you need people, you need others from different fields to help you out with that. I'd like to pass on to V, because you also mentioned working with doctors for the infant warmers. How did that collaboration take place?
Yeah, I kind of, to build off of that idea of with teams, it's critical to have a diverse team from all different backgrounds, because no one person is going to know everything. And so the trick really is understanding what you know, but what don't you know, and finding the right person to complement and fill that gap for you. And so for the infant warmer, I would say what happened was the doctor who led that recognized she needed engineers to help her solve this problem. She knew what the problem was, and she knew, kind of the guidelines of how to solve the problem, right? Get babies warm. But in terms of actually designing and engineering a device, that's where she knew she needed help. And so she reached out to engineers at Berkeley Lab. And although that's not my area of expertise, I've had quite a bit of experience understanding, kind of like Jessica, doing user-centered design. Actually learned from professors at UC Berkeley a lot about that. And so I applied some of that to the stoves work, and bringing that to the infant warmer really helped me understand, okay, how are we going to design something that works? Because a lot of times you end up, as an engineer, I feel like I focus a lot on, okay, how am I going to solve this problem? But just because it solves a problem doesn't mean it's going to solve it the way they want it to be solved. And so one example I had was for our indicator to determine if it's too hot or not. Initially, as an engineer, I'm like, okay, red means hot. We're going to make this a red color, right? And we gave it to the nurses, and the nurses go, what's in this pouch? Is this blood? And I was like, okay, red is not the right color, right? So then we went through the list of, okay, can it be yellow? No, it looks like urine, right? Like you just go through the list, and then finally we landed on orange, and we were like, okay, orange is safe, and they agreed. And so we ended up with orange. If it's orange, it's too hot. So these are the things that you need feedback on from the rest of the team, because you can't, it's hard to see the big picture if you don't have the experience or understand the entire problem. And so team's critical for that.
That's awesome. That's a lot of insight on color. Yeah, and then to ask Jessica sort of a similar question as well. You did, and V, you mentioned having like diverse teams and, you know, bringing in strengths from different fields. Jessica, you mentioned in your introduction about working with, you know, people who know machine learning, other mechanical engineers, and so on. So can you, you know, elaborate more on the collaborations you've worked with?
Yeah, I mean, honestly, collaboration is one of the most fun parts of what I think we're fortunate to do. If you, in actually practicing as professionals in very applied research, the types of problems that we're focusing on usually are quite broad and really require diversity of expertise and backgrounds to solve. And I think that's maybe different from some of our experiences like in school. You know, you and your peers all in one course, and maybe you collaborate on an assignment or a lab, but you're not often, you know, reaching across into other domains and have a project that requires many disciplines to solve altogether. So that's really terrific. It really opens things up to be able to have more impact. The things that we can do as individuals with our personal knowledge are far more constrained than the types of things we can tackle when we have real diversity of expertise to draw upon. So I love it. There's also, as Michael and V both touched upon, the practical dimensions. You know, we work in labs, yet our mission is to bring impact to the world. So how that manifests is necessarily with those who have the boots on the ground in the field to deliver upon what we're trying to improve. And I think that comes up in many facets of the work that we do.
Great, thank you so much. And you just mentioned that in a lab, you're working to solve a solution that you maybe don't have regular or constant interaction with. And also in a classroom, you might be working with people in your own field. So in a classroom setting, when you might be working to solve a solution towards a correct answer, like a predetermined answer in a lab question for your homework or your classwork, how does that experience differ with in the real world in a lab setting where you don't know the answer and you don't know that there is a correct answer, but you have a solution that you need to solve for anyways? So I'll start back with Michael again. How do you go about solving problems where you don't know if there is a solution to be found yet, or if there are many solutions to be found and you have to pick between them?
I mean, and that's kind of fun because that's the switch between what you learn in school in a class and getting to the real world. And it literally in my undergraduate class this semester was the final project where rather than having a fixed solution, students had to design a heating and cooling system for a Mars potential, you know, lander base in the future. And there's no one right way to do it. There's lots of different ways that could work. And in real life, you'd balance costs and structures, but we just looked at heat transfer. And this goes for anything in the lab. There's, you know, often in the lab, we're not just trying to design a product, we're trying to like discover something new. And so we often try to design an experiment that tries to get an angle to view something. You know, usually if it's really easy to see, someone's already done it. And so we have to say, well, what techniques can we do that are new? How do we take a different angle on this problem so that we can see it? So like in spreading wildfires, we know they're going to spread, but we want to understand the why. And then based on that why, can we change something? Can we change a material or do something to prevent it from igniting? And so, you know, there's I think a lot of trial and error just inherent in engineering design, as well as in engineering research that people don't realize. Edison was classic for this in the tens of thousands of designs getting to light bulbs. But I think we try to take a little bit more tuned approach where we try something and then we understand what worked and didn't, and then try it again and do that. And so I think some of the best work we've ever done have been focused on discovering something, and yet we actually found something completely different. And that was what was exciting. But it's the fact that we took a different angle and we tried it in a new way. And we had a reason to do that. You know, we have to think of what's happening and why it's happening. We try these techniques. And then you kind of take what you learn and lead with it. You don't just believe that the answer is going to be what you think it is. You have to believe what data you're getting and then try it again. And so I think learning that process and knowing that what you first try isn't going to work, and then trying it again at different angles is a really important skill to learn over time. And it comes over time. It's not an easy thing. It takes practice and getting used to the to what you want to work not working.
Definitely, yeah, thank you. It's very iterative process to design for a solution. And V, you also mentioned in your previous answer that you got feedback from the nurses when they gave you a different perspective. What are some other tools and feedback that you get so that you know you're going towards the solution that you want, or if you're going in the wrong direction and you need to reconfigure your route?
Sure. I think that, yeah, just honestly, communication and talking to the people who are using whatever it is you're making is absolutely critical. I think it's really easy to think you've come up with the greatest thing ever and then realize that it's not going to be useful to whoever you're making it for. I guess this is kind of a weird analogy, but I guess I look at solving problems as kind of like putting together a sandwich. It's like, how much time do I have and how hungry am I? Right. So if I don't have a lot of time and I'm really hungry, maybe it's peanut butter and jelly, right? If I have a lot of time, then maybe I'll actually take the time to make myself something nice. When I'm trying to get feedback, kind of related to the sandwich idea, right? Maybe I have a friend who I'm like, I just tried the best thing ever. I put pickles with peanut butter or something like that. And maybe I think it's amazing, but I give it to my friend and my friend says, oh my gosh, I don't know what you're thinking. This is a terrible idea. So I feel like solving problems is a little bit like that. It's how much time do you have? And then who are you trying to make this for and make it work? So constantly asking for feedback is key. I will also say that when I go into solving problems, I don't view it as, so there's no failure, right? It's you either learn or you win. And it's really critical to know that a lot of science is really disproving things. It's not necessarily proving things. It's a lot of, I think it's hypothesizing. I think this is going to work. And then you run the experiments or whatever and realize, okay, no, that didn't work. That was wrong. So obviously that's not it. So then you move to the next thing. And the solution you get to is usually what you weren't able to disprove, right? So it's kind of a weird backwards way to look at it, but it's, I don't know. Again, I never view it as failure. It's a part of the process. And when it finally stops failing, or in that view, right, or it gets to a point where you can't disprove it, then you've kind of come across something that might actually be helpful. So
Thank you. That's definitely a great analogy to put it into perspective. And finally, to Jessica, you've mentioned user-centered design in your talk too, in your introduction. So how do you go about solving problems where you don't know if there's a single solution, a best solution, or multiple solutions?
I guess one dimension that I'll bring out is that of, and what I think that a career in research affords is really pursuit of a continuous spectrum of improvement. And a lot of topics or domains where we have a very hard to reach end goal in mind, something like when we think about climate or environment. And one solution's not gonna do it. There's no single silver bullet. And you might also have a single track that you're working on, and for one phase of work, you make a certain improvement and you did better, but maybe you didn't 100% nail it in the technology that you're trying to provide, but you have some success, and it affords the space and time to build on that and to extend the sort of overall state of knowledge and experience, which I think is also very important. We're like, sometimes we don't have the single eureka aha moment, but we're building and continuously improving and learning and disproving along the way. And it's one, I very much appreciate the space and time to do that, versus here's one assignment, now finish it, you're done. It was either, you know, A, B, C, on to the next.
Yeah, I love how you mentioned about, you know, not just the single solution, but continuously learning, continuously working towards something. And so my next question actually relates to learning. The three of you talked about your sort of education pathways. All three of you have PhDs, but I'm wondering, are there careers in the field that maybe doesn't require having a PhD, or what are the benefits of having PhDs? I think the three of you did touch on that, but maybe we'll start with V, because you did mention you were looking at working after a master's and you went back to the PhD for thinking of making a bigger impact. So what can you say are there opportunities in the field that doesn't need a PhD, or and what was the benefit that you got from a PhD?
Sure. On that trajectory where I was working in industry, absolutely not did I need a PhD. It was by many of my coworkers, it was discouraged to some degree. I think maybe one person had a PhD. Most people had bachelor's degrees. Some people had master's degrees. I think for me, the master's degree was nice because it was a year extension from my bachelor's. And I'm not gonna lie, I kind of wanted to stay a student. So I stayed on for the extra year. I wasn't ready to grow up. I don't know if I still am. I feel like the PhD, what door it opened for me was the professor position. I kind of knew that in order to become a professor, you probably would need a PhD, at least at a major university. I know that's not always the case, but for what I was looking at, that was the route I went. Where I am now, Jessica and I work at Berkeley Lab. We work with many people who don't have PhDs. We work with many people who started in one career and are in a completely different career. For example, there's a staff member I work with. He got his bachelor's degree in biology. He started doing an internship up at the lab and decided that he didn't want to do biology anymore. And now he's a software developer doing machine learning. And he hasn't had he's taken classes to learn the machine learning aspect on his own, but he doesn't have a formal degree in that, right? And he's doing very well, very successful, helping us advance research. So I think really going the PhD route, it was more of for me, the question was more, what doors and opportunities does this open, and does it align with where I want to go? It's not necessary, and I'm sure the other two panelists can agree, it's an arduous, long process. Unlike the master's degree, it was like a year where I could kind of extend what I was doing. The PhD is a long process. It was completely worth it, but yeah, it took some time.
I love that you mentioned that you wanted to continue being a student in a master's degree. I kind of did something similar as well. And so I would like to pass it to Jessica, because I remember something that really struck me when you did your introduction was, like, you said you wanted to learn more, and that's how you went into PhD. So maybe you can expand more on that and how that happened.
Yeah, so first was my my ill-conceived notion that somehow I didn't know enough with a bachelor's degree to be a good engineer. That was just, you know, that was false. But I'm kind of glad that I really liked school, the university environment, not necessarily high school. There's a world of difference for me in moving into a university environment. It kind of, you know, fit my sensibilities. I'm always very comfortable on a campus. I don't know, the environment spoke to me. So for me, it was nice. I wanted to learn. I enjoyed the type of learning and structure in graduate school. Even every stage for me was like an improvement upon the prior. Like high school was way better than junior high, and undergrad was better, and then graduate school was like, wow, this is terrific. So for me, that was a lot of the pull. That is not at all to say that it was easy. It was never easy, and I feel like that's one of the places where I was maybe ill prepared. I was like, wow, everybody said you should do science and you should get a PhD and be an engineer, but no one told me how hard it was going to be. And I needed to discover that, just because it was difficult and extremely difficult, that didn't mean that I wasn't good at it or couldn't excel. I think sometimes we have this false notion that, if you're not nailing it at 98 on every problem set and test, or 100, then you're not good enough, and that's totally wrong. So I think speaking back to what V said, the PhD is not required by any means to make great contributions in STEM. There are certain job categories or positions that will have that as a prerequisite. So yeah, if you want to be a professor, then you're probably going to need to get a PhD at some point. I'm probably most proud, that's probably the accomplishment that I am most proud of in my career, honestly. And it does, I think, carry with it, those are credentials, and there's some immediate credibility, and the ring of someone addressing you as doctor is nice, and it carries with it a level of respect and confers that upon you, and that can be a very powerful vehicle and open doors. I'm fortunate though, I work with a team, like across my team of 10 to 15 people that I work with day in and day out. Yeah, a couple have PhDs. Honestly, the majority don't, and they come from very diverse backgrounds, and we collectively make great impact together.
That's awesome. And thank you for sharing about the persistence piece as well. I think it's really important for students in our audience to hear, like, you don't need a 98 and 100 all the time, you can still excel. So thanks for sharing that. And yeah, then I will let Michael talk about PhD. And actually, I do remember that you said, you were encouraged to continue on to the advanced degree. So if you want to expand on that.
Yeah, and I'd say, it's interesting because there's probably been 50 to 100 students. I've maybe been doing it just under 10 years, but at least 50 to 100 students where I've had this long talk of, where do we go? Do we stay with a bachelor's? Do I do a master's? Do I do a PhD? And it's always, an interesting discussion. Okay, so you've made it. You got into a school. You got your bachelor's degree. You're doing a STEM career. Most of the students I talk to are in engineering. And now what? And I just say, there's lots of great jobs with a bachelor's degree. Why did I stay for a master's? They convinced me that, you can do a 1-year master's, you can stay where you are, you'll learn some more, and then you'll go out and get a job and you'll get a little bit more money. That sounds great. I like going to school. Why wouldn't I? And some people, I know students are ready to get out and they can't stand it and they just want to go. And the biggest thing I say is, well, it's always hard to go back. And if you think you might want to go back someday, you might want to do it now before you forget some of the math. But, there are great careers, and I know lots of students who have done just amazing things just with their bachelor's degrees that I've taught, and many I keep in touch with over the years. And I'm impressed with the exciting things. It's not like they don't get to do technical and cool things. Some have built buildings and airplanes and all sorts of designs and invented things. They've started companies. Some have just become big managers that make way more money than I ever do. There's all sorts of paths to go with that. But I think, the master's degree adds a little bit of knowledge. And sometimes it's helpful if you're thinking of advancing on the technical side. sometimes having that master's is necessary in certain careers, you know, to move to that like sort of special expert. But a PhD is really like something different. It depends on the type of work you want to do. I think of all the students I have one master's student out of 15 or so that does research. The rest of them do very technical work, but they're or in business, like in a management position of technical people. But the rest of them, you know, do kind of consulting or design or building. In terms of actual research, there's only one student who somehow slipped into that research role with a master's. Usually you need a PhD, and at a master's degree, it doesn't close any doors. And a PhD, it opens up new doors, but it does close some others. And I think I sometimes describe it as, you know, you're now an expert at doing some really technical hard work. And it was a real challenge to get there. So they're not going to pay you to just do the everyday simple work because it's hard. And so in that way, it does close some things, but it opens up really exciting doors. And I think the biggest change is sometimes, you know, I really encourage you with going to college, take an internship. Don't just do a research internship, take an internship in a company. And a lot of students that I've had were, I am never doing a PhD. I want a job. I want to make money. You know, I don't want to do what you do. And they have an internship and they go, no, I want to stay in school for the rest of, no, I'm done. And then others are like, this was great. I don't want to do research. I really enjoy building real buildings. I want to be in the real world. You know, it just depends sometimes on what you want to do. And every internship's different. But I think having that experience as much as you can before is helpful. And then I've seen many students go that research path because they would just rather be looking at an unsolved problem every day and looking at different approaches versus, you know, the design solutions. There's lots of different types of STEM careers in that way. And so you kind of have to see what do you enjoy the most? I think that's one of the very exciting things. I chose mechanical engineering, by the way, from physics, because it was the broadest engineering and I couldn't make a decision. And then I sort of narrowed in into sort of like thermal fluids, as we call it, you know, combustion, fire, heat transfer, just naturally over time. But I chose ME because it was very broad. But I think within any STEM career, you'll find something similar where you have these choices, and it's not like there's a bad decision along the way. It's just different things you might do in your career. They're all, you know, they're pretty good careers. They pay well. They challenge your mind. They've got good benefits, but it's different in what you do. And I think, you know, that's the thing I try to tell students is for the PhD, you know, you're really doing technical work, you're doing research. Yeah, some people with PhDs go out and they start companies and they become managers or work in government. There's lots of opportunities there too, but they're going to rely on you to be a knowledge expert versus just the designer.
Great, thank you so much for that insight. And on that note, we'd like to ask a question that we ask all our panelists each career talk. So thinking back to when you were 17 or 18, leaving high school or entering college, what advice would you give to yourself as an aspiring scientist/engineer? So I'd like to start back with Jessica, if you'd like to answer what advice you'd give yourself.
I would just give myself my 17-year-old self off to college, like just encouragement, I suppose, that that it will be difficult and in the end incredibly rewarding, satisfying, and gratifying. I would tell myself not to worry about finding exactly the right thing or what, you know, settling on what do I want to do, because there's a discovery process and many things that can make you happy and satisfied. So I wouldn't, you know, I wouldn't sweat so much like what's the major, or should I do this or that, and maybe just try things and take faith and comfort in the fact that the end point is, like I said, quite rewarding and gratifying. I echo Michael's points. It's a good career, high quality of life, good pay, benefits, all of the above.
Thank you. And V, what advice would you give yourself at 17 or 18?
Much like Jessica, I would probably just a lot of encouragement and support. One interesting thing is I didn't know this until after I got my PhD. My high school math teacher told my dad that I would never make it as a mechanical engineer because I was not inquisitive enough or something along those lines. And so when I got my PhD, my dad goes, "Oh, just to let you know." And so I would say, I'm really glad I didn't hear that at 17. But really just, there are a lot of people out there who will think they know what's best for you. But the reality is you will know what's best for you. Follow your heart, follow what calls to you. And there are going to be people who tell you, well, that's not going to work. Or maybe there'll be people who will be supportive and say, yeah, go for it. So my advice to me at that age would have been, don't sweat the grades. Don't focus so much on trying to be the top. Focus more on following your heart, learning what you can, and know that the path will likely be anything but straightforward. There'll be dead ends that you'll have to back yourself out of, and it's okay. It's all a part of the process. Just enjoy the process, and it will guide you to where you need to go. So believe in yourself. It's the short.
Thank you. It's definitely rewarding to prove someone wrong when they were a naysayer in high school. And lastly, Michael, what advice would you give yourself at 17 or 18?
Yeah, I would. It's really hard. I would say one thing would be, interestingly, to lighten up and not worry as much. You take yourself so seriously and so hard. I'd echo about V, about being so concerned about grades. Yes, you should do pretty decent, but I wasn't the straight A kind of student in college until much later, until I really got into upper division, and then kind of was fully sold on ME, and that didn't hinder anything in my later career. But I feel like all those diverging paths of those things that you tried, and you're like, oh, you're wasting time. You're not wasting time. I think that I've used all of those things so much over the years. And it's those broad experiences that really do, form something different. And I've seen it too in, some of the PhD students and the people that I've worked with, like that have had experience in industry or in other careers and other lives throughout. They bring with themselves different skills and different experiences that make them unique and make them able to solve problems that others can't. And so, I would encourage exploring different paths as you go there and follow your passion and what you enjoy learning about and what you enjoy doing. Because if you really enjoy doing it, yes, 70% of your job is still, and I too, I have to grade papers. As much as I love teaching, I don't like grading, but I have to grade, and there's always parts and paperwork, and there's things that you don't like to do, but there's a lot of it that I really love. And I followed, the parts of work that I do that I love. And so a lot of the job is like a hobby, is fun because I enjoy doing it. And I think if you keep following that, then you'll find the right kind of career path. And there's no one right way. People change jobs and things all the time as they move up in their careers. But I think following what you enjoy doing will really bring you there. And you'll see that in college. There's clubs and opportunities. There's competition teams. There's all sorts of ways to try different things along the way. And as you get exposed to different areas, you might find something that really clicks. And I've seen, I even had a fellow engineer who switched and it is now a medical doctor, so people can completely diverge paths over time. You just follow your passion and you'll see what you enjoy.
Great. Thank you so much for your insight, all of you panelists, and thank you everyone for joining us today. This session, as a reminder, will be recorded and uploaded to our website if anyone wants to view it again. And that'll be the end of today's Career Talk. So thank you again for joining us and have a great holiday, everyone.
Thank you.
Thanks.
Thank you.
Thanks.